Oh, welcome and thank you for joining. In this lesson, we'll explore intersections of three planes. In order to best understand how three planes may intersect each other, we need to try to visualize how three planes may be positioned against each other. Recall that the equation of a plane in scalar form is ax plus by plus cz plus d equals 0, where a, b, and c represent respectively the coordinates x, y, and z of the normal to a plane. When discussing the number of possible solutions or the number of common points of intersection made between three planes, we look at the following cases. Case number 1. Three planes intersect at a common point. In this case, there is just one solution to the corresponding system of equations that represent the single point. The coordinates at the point of intersection will satisfy the equation of each plane. The planes are not usually at right angles with each other, so they may make an angle with one another, but what we know for sure is that the normals to the plane are different. Case number 2 is when the three planes intersect at a common line of intersection, and here we notice two subcases. Subcase number 1 is when the common line of intersection between the three planes is made when the normals to the planes are all different. So normals n1, n2, and n3 are different. So the three planes will intersect along a common line of intersection, and there will be an infinite number of points in common, and all these points will lie on this line. Case number 2b is when all the points of intersection lie on a common line of intersection, providing that the planes pi1 and pi2 are coincident. In this case, we say that the normals to planes pi1 and pi2 are equal, but they're different than the normal to plane pi3. And as you can see, since the two planes pi1 and pi2 are coincident, that means that their constants d are also the same. The last case, so case number 3, is when the intersection made between three planes will provide an infinite number of common points that lie all on the same plane. And this happens when the three planes are coincident. In a case like this, the normals to each plane are the same, and so are the coefficients d. So d1 is equal to d2 and equal to d3. The three coincident planes have identical equations which can be reduced or simplified to the same equation. So it makes sense that before we try to find common points of intersection, it is very important that we identify their normals to see if there is any of the special cases that we discuss, because that will gear us towards thinking of the type of solution that we expect to have. For example, if we notice that all three equations will provide same normals, so same coefficients a, b, c, for equations in scalar form, then we're going to say that the planes may be coincident, or they may be parallel to each other and may not intersect at all. And if we notice that two of the planes have same normals, then we have to look into the other cases, so what can produce or what kind of intersections can be made between the planes. So without further ado, I'm going to start, I should say, with example 1. In this example, we are given the equations of three planes, plane pi1, pi2, and pi3. We'll number these equations as equations 1, 2, and 3. Step number 1 to solving or finding the common points of intersection is pairing up the equations to make two systems of equations. So you can pair up the equations in any order you wish. So we can pair up equations 1 and 2, and then pair up equations 2 and 3 together. So it doesn't really matter in which order or which equations we combine with which. So we can combine 1 of 2 and then 2 with 3, or we can combine 1 and 2 and 1 and 3. As long as we have different pairs, then we're good. So I'm going to write the equations right below each other. X minus y plus z equals negative 2, and 2x minus y minus 2z equals negative 9. The second set of equations, so the second system, will be with equations 2 and 3. 2x minus y minus 2z equals negative 9. and 3x plus y minus z equals negative 2. So again, remember in this step, we pair up equations 2 and 2 together, and we make two different systems of equations. It doesn't matter which equations or what pairs we create as long as they're different. Step number 2. We decide which variable we want to eliminate from each set of equations. Remember that we need to eliminate the same variable from each set. So, for example, when I look at the first set of equations, I see that I can easily eliminate the variable y because I see that the coefficients are both the same. And when I look at the second system of equations, I see that y also would be the easier to eliminate. So my decision is that I will eliminate y from both of them. And it is important, again, that we eliminate y from both of them, or x from both of them. So if we eliminate y from the first set, we need to eliminate y from the second. If we decide to eliminate z from the first set, we have to eliminate z from the second, and so on. So in order to eliminate y, we need to subtract the two equations. So we are subtracting 2 from 1. So this will provide x minus 2x, negative y minus negative y is 0y, and z minus negative 2z is positive 3z. Negative 2 minus negative 9 is negative 2 plus 9, and that will give plus 7. So we have negative x plus 3z equals 7. This will be our equation number 4. Don't be scared, we don't have a lot of equations to form. Next, we'll create the new equation by combining these two. So we're eliminating the same variable we said. And this time, we can eliminate the variable y just by addition. So we have 2x and 3x, 5x. Y and negative y will make 0y, negative 2z minus z, negative 3z. And negative 9 plus negative 2 is negative 11. So the next equation we form is 5x minus 3z equals negative 11. So we are going to call this equation number 5. So as you can see now, we created two equations with the exact same variable. So I hope you can understand now why we decided to eliminate the same variable from both. So we'll combine equations 4 and 5. So I will bring 5x minus 3z equals negative 11. And we'll eliminate, or we'll solve the system of equations. Remember, we have only two variables here by elimination. And it seems that the variable z, or the z terms, are ready to eliminate by simply adding the two equations. So negative x plus 5x is 4x, plus 0z equals 7 plus negative 11 is negative 4. So 4x equals negative 4, which means that x equals negative 1. So we have found the value of x. Now we have to figure out the value of z. For z, we can use equation 4, negative x plus 3z equals 7. So negative 1 plus 3z equals 7. So 3z would equal 7 minus 1, 6. So z equals 2. So now that we know both x and z, we can find out what y is. For this, I will use equation number 1, x minus y plus z equals negative 2. With x of negative 1 and z of positive 2, we isolate y, which will be negative 1 plus 2 equals positive 1. Take to the other side, will become negative 3. That will give a value of y equal to 3. As you can see, when solving this system of equations, we found a common point of intersection with coordinates x equals negative 1, y equals positive 3, and z equals positive 2. So we're going to say that the three planes intersect at a common point of intersection with coordinates negative 1, 3, and 2. Stay tuned for more examples as we are going to explore together finding a common line of intersection in different cases. Thank you for learning with me. Bye for now.